Today you are going to be graphing logarithmic equations, and we're also going to be looking at how to solve a logarithmic inequality using that graph. I'll show you what that is here in a little while. All right, so let's go ahead and get started. The first thing we're going to do is we're going to graph y equals log base 2 of x. However, in order to graph that, the first thing we're going to have to do is exactly what we did yesterday, which is to rewrite it in the form of an exponential. So hopefully you guys still remember how we did that yesterday. So I'm looking at this thing right here, and I want to write that in the form of an exponential. So first thing I need is the base. What am I going to use for my base on this one? 2. Very good. So in the first dotted box here, we're going to write 2. That's going to be our base. Now we need the exponents. What are we going to use for our exponent? You got two choices, either the y or the x.
The y.
Very good. Y is going to be our exponent. And of course that's going to be equal to what's left over, the x. So I went from having y equals log base 2 of x to the exponential 2 to the y power equals x. Now what we're going to do is we're going to use this new equation and come up with a table of values. Now notice in this table what they did was they gave us the y values. What we're going to do is we're going to find the x values. So what I need to know is, what do I get when I take this negative 2 and plug it in for y? In other words, what is 2 to the negative 2 power? Put that in your calculator for me. What is 2 to the negative 2 power? 0.25. So write that in your table. 0.25. Now I want to know what is 2 to the negative 1 power. 0.5. What is 2 to the 0 power? 1. What is 2 to the first power? 2. What is 2 squared? 4. And then what is 2 to the third power? 8. All right, so we've just created a table of values based on this equation, 2 to the y power equals x. Now what I want you to do is take these ordered pairs that we just created, and I want you to plot them on that graph paper that you're given. Go ahead and plot those points out. We're going to see what the graph of y equals log base 2 of x looks like. Plot the points.
Oh,
Just plot the points.
okay.
We're plotting the ordered pairs. When you get those points plotted, go ahead and connect the dots. And if you plotted the points correctly, the graph we should be getting should look something like this right here. That right there is the graph of y equals log base 2 of x. We're going to call this our parent function. This is considered to be the parent function of our logarithmic equation. So I want you to underline that for me. This is our parent function. If you look at that parent function, I want to know what is the domain for that graph. What are the x values on this particular graph here? What are the x's? Well, that's only some of them. That's the ones that we came up with in our table, but there's much more than that. Look at the graph over here. What are the x's? Not quite. What? There you go. Notice all the x values are positive numbers. So we're going to say all the x's are x values that are greater than 0. There are no negative x values. They're all positive. What about the range, the y values? What kind of y values do we have on this graph? All real numbers. Notice we got negative numbers, which would be this part that's below the x-axis. But we also have all the positive numbers, which are those that are above the x-axis. So we're going to say all real numbers. So the range for this graph is all real numbers. The domain is x is greater than 0. Again, we're going to call this our parent function. Now what we're going to do is we're going to take a look at a couple of other graphs and compare them to our parent function. So let's take a look at number 2. Number 2, we have y equals log base 3 of x. So what we're going to do first is just like we did on number 1, is rewrite it in the form of an exponential. So the first thing I need is the base. What are we going to use for the base? 3, just like we did yesterday. Now I need an exponent. What am I going to use for the exponent? The y. And what is it going to be equal to? X. So now I have the new equation, 3 to the y power equals x. Now we're going to fill out the table. So we're going to take those values of y and plug them in and see what we get for x. So here we go. 3 to the negative 2 power. What is 3 to the negative 2 power? What did you calculate? 3 to the negative 2 power. 0.1111. What is 3 to the negative 1 power? 0.333. What is 3 to the 0 power? Right? Anything to the 0 power is 1 x. What is 3 to the first power? 3. And 3 squared, you should know what 3 squared is. 3 squared is a 9. All right, so we've just filled out our table. We've just created some points, ordered pairs. What I want you to do is plot these points for me. So go ahead and find these ordered pairs. Plot them for me on your graph paper. And connect the dots. We're going to see what this graph looks like. All right, I think most of you guys got your graph here, and this is what the graph should look like. Notice it's very similar to number 1, but it is different. How is it different? How can we compare the first graph that we got to this one right here? What do y'all notice about this graph compared to the first? Y'all notice anything?
Lower.
It's lower. And why is it lower? Can you tell me what kind of transformation just occurred on that graph, on that current function? What caused it to be lower? Remember, we can move right, we can move left, we can move up, we can move down, we can vertically stretch, we can vertically compress. Ah, there it is. What happened is we vertically compressed. It's like somebody stepped on our parent function and squashed it down a little. We're vertically compressing. What do you think caused that vertical compression? A 3. What do you think would happen if I change that 3 to a 7? It get even smaller, right? We squash it down even more. What if it was a 10? More, right? So the bigger that number is, the more we're going to compress it, the more we're going to step on it and squash it down. All right, so let's take a look at another one. Let's take a look at number 3 here. Number 3, now we're going to take a look at the graph y equals log base 1/2 of x. So the first thing I'm going to do is write down my base. What am I going to use for my base here? Which of these 3 things is my base? The 1/2. Now I need the exponent. What am I going to use for my exponent? Y, like I've done on all the other tests. And what is it going to be equal to? X. So now I have the equation 1/2 to the y power is equal to x. Now let's go ahead and fill out the table. So with your calculator, let's go type in 1/2 to the negative 3 power. But it's 1/2 to the negative 3 power. 8. Now let's figure out what 1/2 to the negative 2 power is. 1/2 to the negative 2 power is 4. 1/2 to the negative 1 power would be a 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. And 1/2 to the second power, or 1/2 squared, is 1/4, or 0.25. Same thing. All right, so we just completed the table. So what I want you to do now is go ahead and sketch me the graph here. Go ahead and sketch me a graph. Plot the points, connect the dots. Let's see what we get. Now, once you get your graph, I want to see if you can find how this graph compares with our parent function. What kind of transformation do you notice there? Did it move up? Did it move down? Did it move left? Did it move right? Did we stretch it? Did we compress it? Did we reflect it? What the heck is going on with this new graph that we've got here? Again, we're comparing it to the very first graph, our parent function. How does this new graph, which I think everyone's got already, it's this graph right here. How does that graph compare with our parent function? All right, Caleb, what do you think? How does that one compare with our parent function, the very first graph? Did we move it up? Did we move it down? Left, right? What happened? All right, very good. Reflection now. Be more specific. Reflection over the x-axis or reflection over the y-axis? Very good. That's exactly what happened here, guys. All we're seeing here is a reflection over the x-axis. And that's because of that 1/2. We got a reflection over the x-axis. All right, so that takes care of the first page. Let's go ahead and take a look at the next page. We've got a couple more to look at. They're going to get a little bit trickier. A little trickier on the next page. Number 4, we want to graph y equals log base 2 of x minus 3. But in order to do that, we've got to first rewrite it in the form of an exponential. So let's go ahead and do that. The first thing I need is the base. Samantha, what are we going to use for the base on this one? Very good, 2. And Mason, what are we going to use for the exponent? 1. Good, 1. And we need to know what it's equal to. So Garrett, what are we going to have it equal to? That's part of it. There it is, x minus 3. All that stuff in the parentheses is what it's equal to, x minus 3. Now notice this is a little different from the one that we did earlier, and that's because we don't have x by itself. So we're going to change that. We're going to make it a little easier on ourselves, and we're going to get this x by itself. In other words, I want to move that minus 3 over to the other side of the equation. The question is, how do you do that? They give you a little hint there. What? You add 3. So now we're going to end up with a new equation, which is 2 to the y power plus 3 equals x. And again, we're doing this so that it'll make things easier for us when we're trying to solve for x. All right, so with your calculators again, we're going to go in there, and we're going to type in 2 to the negative 2 power plus 3. And you can type all of that in at the same time, guys. 2 to the negative 2 power plus 3. What are we going to get? 2 to the negative 2 power plus 3. Now make sure that plus 3 that you type in is not part of your exponent. You might have to hit the right arrow key over so that it doesn't include it as part of your exponent. There it is, 3.25. Let's try it again. This time it's 2 to the negative 1 power plus 3. 2 to the negative 1 power plus 3 is 3.5. Now we're going to do 2 to the 0 power plus 3. 2 to the 0 power plus 3 is a 4. Now we're going to do 2 to the first power plus 3. 2 to the first power plus 3 should be a 5. Remember, all of this you can put in your calculator. Now we're going to do 2 squared plus 3. 2 squared plus 3. What do we get? 7. All right, 7. And then the last one there, 2 to the third power plus 3. Did you get 11? Yeah, that's what I'm getting to. 11. All right, so there's our table. What I need you guys to do now is go ahead and plot your points, and let's see what this graph is going to look like. Let's see what graph we get. Again, make sure you're connecting the dots once you've plotted all the points. Once you get the graph, I want you guys to see if you can determine what kind of transformation occurred on our parent function. Go back and compare it to the very first graph we get. What do you notice? Did the graph move left, right, up, down? Did it stretch? Did it compress? See if you can figure out what the heck happened there. And write it down in the little dotted box. Whatever you think happened, write it down. And by the way, this is the graph that we should be getting. So again, the question is, how does that graph compare with the very first one that we did, the parent function?
Are you asking us?
I'm giving you time to think about it. Give me time to think about it. All right, Alexander, what do you think? What kind of transformation just occurred on the parent function? Move to the right. Be more specific. Move to the right. How many times? 3. There it is. So all we did was move the graph to the right 3 units. Wait a minute. Doesn't this sound familiar? Look inside the parentheses. I have an x minus 3, and I moved it to the right 3. Haven't we seen that before? Look over here on the board. Transformations. Didn't we say with our quadratics, didn't we say with our square roots, with our absolute values, when we subtract, we're going to move to the right. When we add, we're going to move to the left. Remember that? That's still the same thing here? Yep. Still the same thing, guys. Still the same thing. So if that's true, before we even graph this thing, just by looking at this, x plus 4 in the parentheses, what should happen to the graph? It's going to move to the left. How many times? 4 units. All right, so let's see if that happens. Let's go ahead and get the graph. But first, we got to go ahead and rewrite it in the form of an exponential. So the first thing I need is the base, and the base is a 2. Our exponent is going to be the y, and it's going to be equal to the x plus 4. However, just like we did number 4, we want to make sure x is by itself. So I'm going to go ahead and move that 4 over to the other side of the equation by subtraction. So now I've got 2 to the y power minus 4 equals x. So there's a new equation. That's what we're going to use. So again, with your calculator, we want to know what is 2 to the negative 2 power minus 4. 2 to the negative 2 power minus 4. What do you think? What is it? Negative 3.75. Now I want to know what is 2 to the negative 1 power minus 4. Put that in your calculator. 2 to the negative 1 power minus 4 is negative 3.5. Now I want to know what is 2 to the 0 power minus 4. 2 to the 0 power minus 4 should be a negative 3. Now I've got 2 to the first power minus 1, minus 4. 2 to the first power minus 4 is a negative 2. And then the last one, 2 squared minus 4. 2 squared minus 4 should be a 0. All right, so go ahead and plot those points for me, and let's see what the graph looks like. Remember, we said that the graph should move to the left 4 units. Let's see if that's what actually happens. All right, we all got the graph. Here's the graph. And the question is it true? Did the graph move to the left 4 units? Yes, it did.
Yes.
All right, so make sure you write that in the box for me. The graph did move 4 units to the left. So again, all these transformations that we talked about with our other functions, those transformations still hold true when it comes to our logarithmic functions. All right, the last one we have here is the trickiest. This one is a little different from the other 5 that we've done so far. Here we have y is equal to log base 2 of x plus 3. The question is, how is that different from the other 5? Can you see it? How is that one different? Look closely at the equation. What about the plus 3? Notice it's on the outside. All right, so what we're going to do first is we're going to fix that problem. All right, so before we write it as an exponential, I want to move that 3 over to the left-hand side. So what I want to do is subtract. So I got y minus 3 equals log base 2 of x. So the first thing I had to do is move the 3 over. I'm doing this before I rewrite it as an exponential. All right, so now that I fixed that problem, let's go ahead and write it as a exponential. So the first thing I need is the base. What am I going to use for the base? 2, like I've done with the others. Now I need the exponent. What am I going to use for the exponent? Good. Y minus 3, the whole thing. Y minus 3 is going to be your exponent. And what is it going to equal to? X. So now I have the equation 2 to the y minus 3 power is equal to x. So now I can go ahead and fill out the table, get the graph, and see how it compares. By the way, notice that plus 3 is on the outside. What do you think is going to happen to the parent function? What does the plus 3 do to the graph? Move it up, how many? 3 units. So let's see if that happens. Go ahead and fill out the table for me. Give me the graph, and let's see if that actually happens. Let's see if the graph moves up 3 units. Fill out the table. Give me the graph. See what happens. All right, for those of you that are having trouble filling out your table, this is what we should have. So double check your numbers there. Should have 0.25, 0.5, 1, 2, 4, and 8. Now that you know what the numbers are, make sure you give me the graph. Now we've already predicted that the graph should move up 3 units. If that's what happens, write it down in the dotted box. If you see something different happen, then write that down instead. All right, so let's go ahead and take a look at the graph. Here's the graph that we're getting. So the question is, did this move up 3 units? Did our parent function move up 3 units? Yes, that's all that happened here, guys. So the transformation that just occurred here is that we move the graph up 3 units. All right, so at this point, we've taken a look at graphing logarithmic functions, and in order to do that, we had to convert them into exponentials, get a table, plot the points. The question is, can the calculator graph logs? Yes and no. Yes, the calculator can graph logs. However, if you turn to the next page, you'll notice up at the top it says logarithmic functions in base 10 can be graphed using a calculator. So yes, you can, as long as we got a base of 10. Did we have a base of 10 with the first 6 that we did? No. So that's why we had to do it by hand. Okay. However, the next view that we're going to see are going to have a base of 10. So the next view we can use our calculator. So the first thing I'm going to need you guys to do is set up your window to the same thing that they have here. All right. So we're going to set up our x minimum to -2, our x maximum to 10. Scale is 1. Our y minimum is -5. Our y maximum is +5. And that's the window we're going to be using for the next few graphs that we get. All right, once you get your window set up, what you're going to graph for me is log of x. That's this one right here. So go to y equals and type in for me log of x. Then I want you to give me a sketch of what you see on your calculator. Sketch what you see on your calculator for me. Doesn't have to be perfect. This is just a sketch. All right, so if we take a look at that graph, the graph should look something like this here. This is the graph of y equals log of x. Now, right below that, they ask us, how does this graph compare to the very first one we did, that parent function? Look at the very first graph that we did, guys. How does that graph compare to the very first one? Is it exactly the same? No, it's slightly different. The question is, how is it different? What happened? Think about what transformation occurred. Think about what the base is. Think about what we said about that base.
It's not being compressed.
It's not?
It is.
I'm asking you.
It is. Oh, it is because it has.
I think we even mentioned this number. First one we did had a base of 2. The second one we did had a base of, now look at number 2. Everybody look at number 2 for me real quick. Notice how we had a base of 3. And what happened to that graph when we changed that base to a 3? It got smaller. What did we say transformation occurred? Vertically compressed. We said the bigger that number is, the more we're going to compress it. What base are we using on our log right here? 10. So what is that 10 doing to the graph? It's compressing it. Okay, so I need you to write that down for me. This graph right here is being vertically compressed, or the parent function is being vertically compressed. I also want to point out the fact that both of the graphs, this one and the parent function, has the point 1, 0. So write that down for me as well. They both have the order pair 1, 0. Anybody remember what we call this kind of log when we have a base of 10? We had a name for this. What's that? Nope. In your notes. You got your notes right there.
What was the question?
The question is, we had a name. There it is. Common log. Remember we said we refer to these as common logs whenever we have a base of 10, which is exactly what we have here. All right, so let's take this a step further. Let's take a look at the next one, number 8 here. What they want us to do is in y equals, we're going to type in 4 different equations. So in y1, we're going to type in log of x, which you should already have. In y2, we're going to type in 3 log of x. Then we'll type in 5 log of x, and then we'll type in negative 0.5 log of x. All right, so go ahead and get all those in for me. Graph it, and sketch what you see on your calculator onto your paper. Yep, catch all four. All right, so here's the graph that we should be looking at. That's the graph of all four of those functions there. The first thing they ask us for is, what do they have in common? What do you notice about all four of those graphs? What do they have in common? Well, they're all the same shape, but what else besides that? And what is that 1 point? 1, 0. Notice all four of these graphs go to the same point, which is 1, 0. So write that down for me. They all go to the same point. How are they different? How are they different? What do you notice different about them? Well, look, guys, here, it's kind of hard to tell, but this graph right here is going to be that graph there. The second one is going to be this graph right here. The third one, that's going to be this graph right here. And this one right here is going to be this graph. So how are they different? What do we notice?
Some get bigger.
Some get bigger, and why are they getting bigger? What are we doing to them?
It's less than 10. Like the base is less,
Okay.
and then the negative, that's why it's reflected.
All right, so there's one that's being reflected. Let's write that down. That's how they're different. One of them's being reflected. What else? What do you notice about these two equations, 2 and 3? What do they have in front of that log? The 3 and the 5. What do you think that 3 and 5 is doing to the graphs?
Making it bigger.
Making it bigger. And what's making it bigger? We are vertically stretching. Okay, so not only do we see some reflection, but we also see some stretching and compressing. Okay, so those are the three things I want you to write down. We see some vertical stretching, some vertical compression, and we also see some reflection. Anybody know what's causing the reflection? The negative. Just like all the others functions that we looked at, the negative gives us a reflection over the x-axis. All right, let's take a look at one more set here, number 9. So again, we're going to go to our calculators, and in y1 we're going to type in log of x, which we should already have. In y2 we're going to type in log of x plus 2, log of x plus 4, and log of x minus 4. Well, let's see what happens. Let's not forget, guys, even though you don't see the base, it is there. What is the base that we're using? 10. That common log. All right, so again, we're graphing all 4 of these, and those 4 are going to look something like this right here. So the question is, what do these functions have in common? Do you see anything they have in common? Anything they have in common, all 4 of those?
Yeah.
All the same arc.
They all have the same arch or the same shape, and that's good. Anybody notice anything else besides they have the same shape?
They're all
So number 9. What's that?
They're all on the line.
They're all on this. Sorry. They don't touch 0.
Oh, wait, are you talking about different?
Yeah, right now we're talking about whether they have the same.
Same base.
What is that? Ah, they have the same base. And what is that base? 10. All right, let's write that down. Notice all of these equations all have the same base, which is 10. Very good. Let's go ahead and take a look at how they're different. How are they different? What do you notice here?
They're different. Start different.
They what?
They start.
They start in different places. And why do they start in different places?
Because of the y, not the y understood. No, not, what's it called again?
I don't know. You tell me. All I'm asking is, why are they starting in different places? What's causing that? The plus 2, the plus 4, and the minus 4. Okay? So, the graphs are being vertically shifted. In other words, some are being moved up, some are being moved down. Can you tell which is the one that's moved down? Which equation? Minus 4. The minus 4. The minus 4 moved it down, and the other two have been moved up. All right, so that takes us through number 9. Now we're going to see if we can summarize what we've just learned here. So, the equation y equals a times log base b of x minus h plus k. Let's start with the a. What exactly is a doing to our graphs? Well, it depends on what a is. If a is a number greater than 1, what's going to happen to the graph if a is greater than 1? Stretching. What kind of stretching? Vertical. We got a vertical stretch. If a is some number greater than 1, we're going to stretch it out. Of course, the bigger the number is, the more we're going to stretch it out. What if the number is between 0 and 1? What's going to happen to the graph? We got it. If it's bigger than 1, we're going to stretch it. So if it's between 0 and 1, we're going to compress it. What kind of compress? Vertical. Vertical compression. What if that a is a negative number? Something less than 0. What does the negative sign do? Reflect over x-axis. It's going to give us a reflection over the x-axis. So the same things that happen with our quadratics, our square roots, our absolute values, it's going to occur here as well. Now, as far as the b goes, our base, it's going to do the same things. It's going to stretch vertically, it's going to compress vertically, and it can also reflect the graph, depending on what the number is. So it does the same thing as a. It stretches, compresses, and reflects. All right, now the h, notice the h is inside the parentheses, and when it's inside the parentheses, you'll notice the transformations over here. We're either moving left or right, depending on what we're doing here. So let's start with subtraction. If we're subtracting, what's going to happen? Which direction are we going to move? If we're subtracting, we're going to move to the right. But if we're adding inside the parentheses, we're going to move to the left. And the k, that k is on the outside. Anytime it's on the outside, we're going to move that graph either up or down. So, subtraction. Would I move up or down if I'm subtracting? Down. And if I'm adding, we're going to move the graph up. I'm going to move that parent function up. So again, everything that we talked about with our other parent functions, that's the same thing that happens with our logarithmic functions. All right, so that takes care of graphing our logarithmic functions. Now let's take a look at the last page. We've got one last thing to look at here, and that's inequalities. Now here it says in order to solve a logarithmic inequality, we're going to do a couple of things. The first thing we're going to do is take the left side of the inequality, put it into y1. We'll take the right side of the inequality, put it into y2. We'll graph to determine where the inequalities hold true. And we're going to do that by finding the intercepts, or the intercepts. And then we'll check with our table and pay attention to the domain. So let's take a look at a couple of them here. We're starting to run out of time, so we'll try and at least get 2 done. All right, so here we go. Number 11. Number 11. I want to know what is the solution to this inequality. So the first thing we're going to do is in our calculators. Oh, by the way, let's go ahead and reset our calculators. Not reset them, but change our window. And you can change your window by going to zoom number 6. Zoom number 6 is a standard window. We don't need that window that we used earlier anymore. All right, so now that you've adjusted your window, we're going to graph this inequality. So what we're going to do is in y1, we're going to type in the left side of the inequality, and in y2, we'll type in the right side of the inequality. So go ahead and write that down for me, and then type it in your calculator. Remember, we're using both y1 and y2. What we should see is two graphs. We're going to see our logarithmic graph, and we're also going to see a horizontal line. And that horizontal line is representing that 7 that we put into y2. Now, these two graphs that we get, they're going to intersect. So what I want you to do is, I want you to find the point of intersection with your calculator. Now, remember how to find the point of intersection, right? How do you do that? Second trace, number 5, enter, enter, enter. So find that point of intersection because it's part of our answer. All right, we should be getting something that looks like this right here. This is the graph, and that point of intersection occurs at the order pair 4, 7. That's our point of intersection. So what we're going to do is find the solution. So we've got part of the answer. So down here at the bottom where it says final answer, we're going to write x, and we're going to write 4. That's where they intersect at, 4. That's this point right over here. Now, what we need to keep in mind is we're looking for when the y values are greater than 7. So we're looking specifically at this part of the graph here. This is the part of the graph that I'm looking at. So the question is, if I'm looking at that part of the graph, are the x values greater than that 4 or less than that 4? I'm looking at this part of the graph. Greater than or equal to. Okay. So the solution to this inequality are all the x values that are greater than or equal to a 4. Now remember, they said that we can double check this with our table. So if you look in your table, here's what we're going to see. I want you to pay special attention to the x values 4, 5, and 6. Notice how 4, 5, and 6, all of those are either greater than or equal to the 4. But more specifically, notice how the y values over here are either 7 or bigger, which is what it said up here in the inequality. We're looking for y values that are greater than or equal to the 7. And that's where they occur. All right, let's take a look at one more here, number 12. Number 12. We're going to do the same thing for number 12. We're going to put the left side of the inequality into y1. We'll put the right side of the inequality into y2. Graph it, and find where they intersect at. So let me give you some time so that you can put that in your calculator. Find the point of intersection so we can find our solution. All right, guys, again, find that point of intersection for me.
Mine's an error. Oh, I put a negative.
Just like the first one, you should be getting two graphs. You're going to get a graph of your log. You're also going to get a horizontal line. We want to find where these two lines or these two graphs intersect. That point of intersection is important for us. It's part of our answer. All right, so the graph that we're getting should look very similar to what I have on the board here. And if we find the point of intersection, we should find that they intersect at 1.165914438. That's important for us. That's this intersection point right here. So down at the bottom, I'm going to come over here and write x. And that 1.16. Now remember, we're looking for values that are greater than or equal to 3.8. So I'm looking specifically at this part of the graph above the horizontal line. Okay, because it says greater than, so I'm looking above the line. So if I'm looking right here above the line, what kind of x values do I have? Do I have x values that are greater than that 1.16 or less than that 1.16? Less than. We're going to the left here, so it's less than or equal to the 1.6. Okay, so the x values are less than or equal to 1.6. However, we've got another problem. This graph that I have here, is it ever going to cross over the y-axis? No. And if I leave my answer like that, that would also be including some negative numbers. Do I want to include negative numbers? No. So I want to put in my answer over here that I'm not going to include negative numbers. So here's how we're going to do it. We're going to say that the x values also have to be greater than 0. Greater than 0. We don't want any negative x values. Therefore, the solution in number 12 are all the x values between 0 and 1.16. All right, guys, we're going to go ahead and stop right there.